Carlos Gómez Cabello from the University of Sevilla. He will speak on one parameter semigroups of composition operators on the space H2 of Dirichlet series. Please, Carlos.
Okay, thank you for the introduction. And also, I would like to thank the organizers for the opportunity of serving this piece of work with you. This talk is based on a joint work done in collaboration with my PhD supervisors, Professor Manolo Contreras and Professor Luis Rodriguez Piazza, both from the University of Sevilla. Okay, so I'm going to start recalling some basic definitions which shall appear throughout the talk. So if I have a domain omega in the complex plane and I have a family of holomorphic functions defined from omega into itself, we say that this family is a semigroup if the following two properties are satisfied. First, phi 0 is the identity map in omega. And second, we have the following relation for the composition of the elements. Similarly, we can define the notion of semigroups in the context of bounded operators between Banach space X, and we say that this family is a semigroup if T sub 0 is the identity map, the identity operator in the Banach space X, and the same composition rule holds for the family of operators. In the case of semigroups of holomorphic functions, if we have that the semigroup converges to the identity uniformly on compact subsets of omega as t goes to 0, on the right-hand side, we say that the semigroup is continuous. And in the case of semigroups of operators, we say that the semigroup is strongly continuous if we have convergence to the identity in the strong operator topology. That is, this limit occurs in the norm of in the topology of the norm of the Banach space. Okay, so there is a way of linking these two notions. This is done through the composition operators, which are defined as follows. If I have a semigroup of holomorphic functions in omega, we can define for each t the composition operator of symbol phi t. That is, we compose the functions f of the Banach space X with the holomorphic functions phi sub t. This allows us to consider these two objects simultaneously and study the properties of one object through the properties of the other one, and vice versa. So I'm interested in discussing the Bergson and Porta theorem in the setting of the Hardy space of Dirichlet series. And let me recall what did Bergson and Porta proved in their seminal paper from 1978. They showed that given a family of holomorphic self-maps of the unit disk, this family defines a strongly continuous semigroup in H2 of composition operators, if only if the semigroup of symbols is a continuous semigroup in the unit disk. So this result was later generalized to HP, also to the Bergman spaces, the Dirichlet space. And as I mentioned before, the plan is to see what happens when we look at this result in the Hardy space H2 of the Dirichlet series. So this is a little bit the outline of the talk. I'm going to, for those who might not be familiarized with Dirichlet series, I will recall some basic notions related to these objects and mainly see what changes when passing from Taylor to Dirichlet. I will then present the space H2 and also recall or present some results of the composition operators, or the bounded composition operators in H2. We will then consider the semigroups of composition operators in H2 and see this Bergson and Porta result in this space. And then we will say some words about the infinitesimal generator of the semigroups. So this is very well known to all of you. Given a Taylor series, which is a formal series of this form, we can associate to this series several magnitudes. We can consider R1 as a near number, real number, positive real number of infinity, for which the series converges in the open disk of central 0. and does not converge outside the closed disk. Similarly, we can define a quantity R2 for the absolute convergence, and we can define analogously a third magnitude for the uniform convergence. The thing is that these a priori different radii of convergence happen to coincide, and we call this the radius of convergence of the series. And not only this, but the series defines a holomorphic function in the open disk. So what happens when we move from Taylor to Dirichlet? So well, first of all, I will use the notation C theta, C sub theta, where theta is a real number to denote the complex numbers whose real parts are greater than theta. And C plus will denote C naught, C0, the right half plane. So a Dirichlet series is a formal series of this form where we have a complex coefficients times n to the minus s, where s is a complex variable, and we take the sum on n for n between 1 and infinity. For instance, maybe the most popular Dirichlet series is the Riemann zeta function, which consists of taking all the coefficients equally constant to 1. But okay, for instance, where does this representation hold, in which half planes, etc. So in order to study the Dirichlet series, we associate to these objects several abscissae of convergence. We define the abscissae of convergence as the infimum of the real parts for which the series converges, and it happens that the Dirichlet series, the function defined by the Dirichlet series, is holomorphic in the half plane defined by the abscissa of convergence. We can analogously define the absolute convergence abscissa and the uniform convergence abscissa. We have this relation between the abscissae. Notice that we have less or equal, which, and as we are about to see, they need not coincide, these abscissae. And in fact, there is also a restriction between the separation between these abscissa. That is, the absolute convergence abscissa is less or equal than the convergence abscissa plus 1. That is, as soon as the Dirichlet series converges, pointwise in certain half-plane, it will converge absolutely eventually at the half plane, which is 1 unit to the right. And it is pretty easy to give an example of a Dirichlet series for which these abscissae do not coincide. For instance, if we consider this alternating zeta function, we can see that the convergence abscissa is 0, whereas the uniform and absolute convergence abscissa are equal to 1. So, okay, I will use this notation, this D, to denote the space of convergent Dirichlet series. So the Dirichlet series of this form with convergence in sub half plane. So we have had some change of language from when passing from Taylor to Dirichlet. The radii of convergence become abscissae, which in fact, in the case of Taylor series, these radii were the same. And in the case of the Dirichlet series, these abscissae may differ. And of course, the abscissae give rise to convergence in half plane instead of convergence in disks, and the holomorphicity is in the convergence pointwise convergence half plane. Okay, so let me introduce now the Banach space, actually the Hilbert space of Dirichlet series we will be considering this talk, which is the space H2, which in fact was introduced in 1997 by Hedelman, Lindquist, and Seip. Let me mention that they introduced this space to solve, or in their work from 97, they introduced this space H2 and also H infinity to solve a problem related to a problem arising in an harmonic analysis, and they follow an intuition mentioned by Berling in their collected papers. So the space H2 is the collection of the formal Dirichlet series for which the coefficients are little L2 summable. So with this definition, we obtain a Banach space of analytic functions in the half plane C1/2, since the absolute convergence abscissa is less or equal than 1/2, and this is actually optimal. So there are meaning that there are Dirichlet series in this space defined in C1/2, which cannot be defined further. And this is also a Hilbert space with the expected scalar products between two vectors of this space with the little L2 scalar product. Okay, so having this in mind, one of the most studied operators in the context of Banach spaces of analytic functions is the composition operator. How will we define this operator in the setting of H2? So we consider a analytic function from C1/2, that is the complex numbers whose real parts are greater than 1/2, and define this operator in H2 by composing every function f with the symbol with the function phi, which we call the symbol of the composition operator C phi. So a natural question in operator theory in the setting of Banach space of analytic functions is describing the symbols which define bounded composition operators. So in relation to this matter, we have here the Gordon-Hederman class, which consists on those holomorphic functions from the red half plane into itself, which satisfy the following two properties. First, they admit this representation. They can be written as a C phi times S plus a Dirichlet series little phi, where this constant C phi is either a natural number or zero. We call this number the characteristic of the function phi. And in the case C phi equals zero, which could happen, then since H2 is defined, the elements in H2 are defined in C1/2, we ask the symbol phi to map the right half plane into itself so that the composition operator is well defined. Okay, so what did Gordon and Hederman prove in 1999? They showed that for a holomorphic function, to define a bounded composition operator in H2, this symbol must have a holomorphic extension to the whole right half plane belonging to the Gordon-Hederman class G. And actually, this is a necessary and sufficient condition. So it might be shocking at first sight that this is actually the condition, since H2 is a Banach space of holomorphic functions in the half plane C1/2, and we ask the symbols to be actually extendable to the whole right half plane. So what is going to be then what are we interested in? What is the problem we are going to consider? So we are going to take the Banach space H2, and we are going to also take a semigroup of phi t of holomorphic functions in this class G, in this Gordon-Hederman class G, and also the associated family of bounded composition operators in H2. They are bounded because by Gordon-Hederman results, these symbols, we are precisely taking the elements of the semigroups in the class of symbols defining bounded composition operators in the Hardy space H2. And I recall Bergson and Porta, they showed that in the setting of the unit disk, the sub T is a strongly continuous semigroup in H2 if only if the semigroup of symbols is continuous. So we want to see if we can prove a similar result. Let's say a sort of Bergson and Porta theorem in the setting of the H2 space of Dirichlet series. So this is what the result looks like. We have that if we consider a semigroup of holomorphic functions, phi sub t, where each element belongs to the class G, and we consider the associated family of composition operators, then the semigroup of composition operators is strongly continuous in H2 if only if the semigroup of symbols is continuous. And in fact, we have, this is very specific from the Dirichlet series setting. We also have that these two statements are equivalent to the convergence to the identity in the whole, in every half plane strictly contained in the right half plane. So we recall that we said that for us, being a semigroup being continuous means that we have convergence to the identity uniformly on compact sets of C plus in this context. And we have that, in fact, this is in the context of continuous semigroups in the class G, this is equivalent to the convergence in every half plane C epsilon. So I'm not going to give the proof of the result, but I want to share with you some comments. As I mentioned, the equivalence between B and C depends strongly on the properties and the structure of the class G. So this is not true in general. This is not true for continuous semigroups in the right half plane. It is easy to see if we consider, for instance, this example. We have that it is a continuous semigroup. It satisfies both the algebraic properties and it converges to the identity uniformly on compact sets of the right half plane, but it fails to satisfy C. And the implication between B and A follows from a compactness argument. I want to mention something regarding A implies B, which in the case of Bergson and Porta's theorem follows pretty easily, since the NOR convergence implies local uniform convergence. So if I have a sequence of composition operators in H2, a family of composition operators in H2, which converge to the identity in the strong operator topology, then the symbols convert to the identity uniformly on compacta. But this is not longer this is essentially using as a test function the identity map. But the problem we can test the identity map, and the semigroup structure in fact plays no significant role in this implication. But what is the problem when we pass to H2? Well, the first problem is that the identity map is not cannot be represented by a convergent Dirichlet series, and in fact, this implication is not longer true in this setting, and actually we can build a counterexample. So Kronek's theorem allows us to find a sequence of real numbers converging to identity when n tends to infinity, and such that m to the minus ix of n converges to 1 as n tends to infinity for every m. So if we consider this family of symbols, which are actually in the class G, s plus ixn, and consider the associated family of composition operators, then given a Dirichlet series in H2, we can see that the family converges in the strong operator topology to the identity, but we do not have that the symbols converge to the identity, not even pointwise. So it is the semigroup structure, which in the case of the unit disk play no significant role here, is crucial in the proof of Bergson and Porta's result in this setting of Dirichlet series. Okay, so now we have shown the Bergson and Porta's theorem in H2 in this space H2, but what happens with examples? Can we provide non-trivial examples of continuous semigroups belonging to the class G? For instance, if we consider the translations trivially are a trivial example or elementary example of a continuous semigroup in the class G, but are there other more involved examples in the class G? In order to answer these questions, we have to go to the classical theory of continuous semigroups developed by Bergson and Porta in their seminal paper, and from 78. And let me recall, probably when we talk about Bergson and Porta's theorem, specialists may have in mind this theorem, in which they gave a description of the infinitesimal generators of the continuous semigroups instead of the theorem I stated at the beginning of the exposition. And what they showed in that same paper is that if we consider a continuous semigroup of holomorphic functions, then in the right half plane, then the following limit exists for all s when the limit is taken locally uniformly in the right half plane. And not only that, if we fix a point in the right half plane, then the trajectories, that is the map associated to phi sub t of s, is the solution of the following Cauchy problem. So clearly the function h is holomorphic and maps the right half plane into a complex plane, and we call it the infinitesimal generator of the semigroup. So the thing is, are we able to describe which are the infinitesimal generators associated to the continuous? We have the description of the continuous of the infinitesimal generators of the continuous semigroups in the class in the right half plane. So can we do it for the continuous semigroups in the class G? That is for this subclass of the continuous semigroups in the right half plane. So let me sketch a little bit an strategy in order to answer this question. So we are going to consider a continuous semigroup phi sub t in the Gordon-Heidelman class G with infinitesimal generator H. Let H be its infinitesimal generator. Okay, so actually, I did not mention this before, but when we consider continuous semigroups in the class G, the characteristic of all the elements, remember that in the Gordon-Heidelman class, they are functions of the form a natural number or zero, S plus a Dirichlet series. I did not say anything about this, but it occurs that all the elements of a continuous semigroup in the class G have characteristic equal to 1. Okay, so all the elements of the semigroup phi sub t are of this form. So by definition of H that I presented in the previous slide, we have that H is a local uniform limit of this Dirichlet series. So one could wonder if the local uniform limit of Dirichlet series gives a convergent Dirichlet series, but this is not the case. Why not? This is follows from a result proven some years ago by Aaron, Bayard, Gautier, Maestre, and Nestoridis, where they show that given a simply connected domain, and then the Dirichlet polynomials are dense with the local uniform convergence in the holomorphic functions in omega. So in general, the limit is not going to be a Dirichlet series. But there is another remark, and the remark is that Barjula-Karateori lemma, we have that the Dirichlet series involved in the definition of phi sub t. Remember, phi sub t is S, the identity map, plus a Dirichlet series, phi sub t maps the right plane into its closure. So with this extra assumption on the maps on the Dirichlet series, little phi sub t, we indeed have that the local uniform limit of Dirichlet series mapping the right plane into itself is a Dirichlet series. So if we consider a sequence of Dirichlet series mapping the right half plane into itself, converging uniformly on compacta to a function phi, on compacta of the right half plane to a function phi, then this limit function phi is a Dirichlet series. So we have that H is a Dirichlet series. What we have shown? We have shown that if we have a continuous semigroup in the class G, then its infinitesimal generator is necessarily a Dirichlet series. And this is in fact an equivalence. That is, if I consider a allomorphic function from the right half plane into itself, into the closure. So I consider this function in this way in order to ensure that the semigroup is going to be the resultant semigroup is going to be a continuous semigroup in the right half plane. So what are the extra assumptions that H needs to satisfy in order to ensure that this continuous semigroup in the right half plane is in the class G? So H is the infinitesimal generator of a continuous semigroup of elements in the class G if only if H is a Dirichlet series. And in fact, this is equivalent to H being a Dirichlet series bounded on every half plane, strictly contained in the right half plane. So let me just give a few comments on the proof. A implies B. We have just seen the idea of the proof in the previous slide, and B implies C. This follows from this is a general result from Dirichlet series theory, and maybe the most interesting implication is C implies A, and the most surprising. The idea of the proof is to use a Cauchy-Picard type argument. So consider a suitable complete metric space and define an operator so that it is contractive, then it has a unique fixed point. And with this, we can show that this fixed point is going to be of this form. So this is the idea of the proof, because okay, why, as I say here, why H being a Dirichlet series ensures that this is the resultant semigroup is of this form. So this is given by a Cauchy-Picard type theorem. So remember the question I raised. This is, are there non-elementary examples of continuous semigroups in the class G? So the answer is that actually there are many continuous semigroups in this class. So how can we build? Not only this, we know that the answer is we have a rich class of examples, but we also have a say way of building explicit examples. So we can, for instance, we take H satisfying the desired properties, holomorphic function, mapping the right half plane into disclosure, and such that it can be represented as a Dirichlet series. We solve the initial value problem, and we posing phi sub t of s equals y of t, we obtain the example. So, for instance, considering a very simple holomorphic function h satisfying these properties, that is 1 plus 2 to the minus s, and repeating this, doing this process, solving the associated Cauchy problem and calling phi sub t of s to the solution, we obtain, for instance, here an explicit example of a continuous semigroup in the class G. And actually, when we were able to prove this theorem, we felt quite relieved, because for quite some time we thought that the only continuous semigroups in the class G were the translations, and we thought that we had proven all this Bergson and Porta theorem in H2 just for elementary semigroups. And this is essentially all I wanted to share with you today. And thanks a lot for your attention.